see.
You have come
We'll
on.
see the Jordan canonical form of the Bible. We'll see how that works out. I don't know the Jordan canonical form.
I don't think we can pass that.
I take it right? And then I kind of like let go. And then on the final, I take it. Just after not do my thing. Well, again, like by mental standards, garbage. So like, no big. It's just that I go back to prison. Well, I have 4 courses, but I don't have like.
Right, so we can finish the proof, then 2 more examples, and on Friday we're gonna start the review. So we already talked about that when you're diagonalizable, you can decompose your space into your eigenspaces, but it's only for diagonalizable. And for general linear maps, you can still say something interesting, but you have to use what is called generalized eigenvector. Okay. And now we're going to prove the Jordan form theorem. So you can find the basis B so that you can write it in what are called Jordan blocks. And each of the blocks has the eigenvalue in it, and ones and zeros above that. Okay, so let's start the proof. Today will be more abstract than Wednesday. Tomorrow we'll do examples, and then Friday more examples. So this is like the last proof. So yeah. We can show that if you give me any Nilpotent map, then I can give you vectors V1 to Vk, and I can form cycles, right? So that one. so that they form a basis, and the very last element is always zero. So we have this beautiful picture. So you have stuff like this, like that. And you know, you have V1, dot, 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 NM1, V1, V2, NM2, V2. And I mean, here goes VK, and then VK. Yeah.
V1 and V2, right? But if you act on them with N, they both get mapped to the same number.
No, if you add with N, they go to zero, because. Yeah. So if you, no. I don't understand what you're saying. Kernel of who? Kernel of who? Okay, yeah. Yes. Well, I don't know if this is true. Oh, yeah, from this picture, yeah. Sorry? Yeah, the number of boxes on the first column is equal to kernel of M. I have no idea what you're talking about. Just to be clear, N of V1 is not zero. But all these guys are zero and they're linearly independent. And we can prove that. Yeah, there's zero. N of Mi, Vi is zero. Yeah. Yeah. So I think we talked about this. So the matrix representation of implied by this is the following. So again, you have to write them from decreasing powers because you want upper triangular. So let's look at A1. A1 corresponds to the first cycle, okay? So in the first column will be N of who? Who do I have to compute here? The coordinates of what vector? Huh? No. Yep. So and which is what? Zero. So the first column would be zero. Second guy is N of M1 minus 1 V1, which is N of M1 V1. So you put a 1 on the first. Okay, so that's the game. And the reason we study this is because we talked about this. This map T minus LJI to the K is nilpotent, and is nilpotent to the dimension of the space. So dj, dimension of this eigenspace. Okay. So this guy is the zero map. Restricted. We always have to restrict. Yeah. So then that's how we get Jordan form. So the width of the proof will be what we do now. I think we talked about this. I have this rule. Okay. But okay. We've done so many inductions. I don't know how many. All right. Let's do it. So for dim1, oh, this is interesting. Yeah. So why is it immediate that when dim v is 1, then there exists a basis so that n of b is just zero. A zero number. In other words, why in dim1 we have that n is the zero map? If it's not one. Yes. Yeah. Let's see. So nk of x is 0. And what do you want to say? What's my question? Oh, now I do. Sorry. Yeah. So, wait, is that what you're going to say? That you only have a single guy? No, just a second, just a second. So nk of x is in the span of x. Like take a fixed guy as a dim v, and this guy is 0, and but then you take any other element, a of x naught, then what is that? I think that's what you said, right? Yeah. This is ak nk of x naught, but this is 0. Yeah. So because you want to do it for every you want to do it for every. Oh no! This is all garbage. No, the proof is much simpler. I'm sorry. We proved the result. We proved that the nilpotency degree is less or equal than dim v, which is 1. And so n of 1 of x is 0 for all x. That's what happens when I ask a question. I have the proof in my head, but I don't like the answer because I want you to answer it. But then I forget the answer. And now I have to recall the answer. We proved that in class. It can only be 1. If it's 0, it's the identity. So, all right. So, then can we put the cycles in any order? No, that's a good question. He asked on Piazza, and my answer was you don't get upper triangular anymore. So, if you switch a single vector, suppose you switch the first two, then whatever, you will get a 1 like down here, right? Because you switch the ordering. Is that okay? So you don't get upper triangular anymore. You don't get canonical form. Is that okay, Joshua? So suppose you have by induction that you have it for every subspace, but not V itself. Okay. So you build the basis so that n restricted at U, evaluated at B, call it U, is a Jordan form. Okay. So this is the restricted guy. But yeah, so we want to go from the smaller space to V, so you have to make a smart choice for you that will allow you to extend. N is nilpotent, so it's not subjective. Can you guess very quickly why? Yes. And why is it not injective? Yeah, so, and why does he have non-zero kernel?
The dimension of the dimension of the image.
All right, let me do. So you have n of k of x is 0, right? For some k, for all x. And then what do you want to do? You want to write this as n of k minus 1x. And because k is the smallest, this guy is not 0. And so the kernel of n is not empty. Good. Yeah, so that means you got your strict subset. That's the whole point of it. Because if you have surjective, you could be V, and you don't want to be V, because you want to apply the induction hypothesis. Does that make sense? Okay. So you have your vectors, you have your M1 and K, and you have a cycle, but for the restricted space, U. And this is a small choice because U is the image of N. So this will allow you to go one layer back and extend. Okay, so let's do that. And that's the main trick. That is image of N. So all these vectors have one layer behind them. Okay, just okay. All right, all right. Okay, now since U is image of N, each of these VIs is equal to N of UI for some UI, right? Because we're in the image. And so you further extend as follows. You first rewrite all the cycles in terms of UI, but that still might not be enough. So you have to further extend by W1 to WP, okay? Now this guy is a basis for V. Just to see if you know, how do you, if somebody gives you a basis, how do you extend to the full thing? No. I mean, we'll come back to this in a review, but yeah. Yeah, start, I need the, okay, go ahead. Yeah, but concretely, I give you like a space, like 5 dimensions, and I give you 3 basis vectors. How do you go to the full thing? How do you make a choice? And let's say I even want to go for normal. Well, I mean, I start with 3 guys that are orthogonal, and I want to get 5 that are orthogonal. How do I do it? When you say pick, how do you pick it? What do you mean heading? What if it's in the? No, you can't just. So how do you pick the next guy? Yeah, you can't just go like. But you have 3 of them. You want 5. No, you suppose they're already orthonormal. How do you get 5? Cross product? Yeah, that's the main idea, right? You want to look at the orthogonal complement, right? So you start with 3 guys, and you want to find the guy who's orthogonal to all 3 of them. Hopefully, you can do this by eye, meaning you have your 3 vectors, and then you can like sort of see, okay, they have zeros there, so let me put a 1 and 0 everywhere else. Like you said, yeah, exactly. But in practice, it won't be that easy because your basis might be polynomials, or you might be matrices, or there might be something disgusting. So either you do this, you move to Rn and you turn a guess, or you figure out the complement for all three of them. So you get a system, you get three equations, and yeah, you get three equations, right? No, you get three dot products. You get x v1 is 0, x v2 is 0, and x v3 is 0. And this one. So either way, depending on how complicated the problem is. The easiest is, of course, to map it, I don't know, easiest, whatever you find most comfortable. If you can map it to a red and guess, but they might have full numbers. They might have like 1 minus 1, 2, 3, 4, and then, right, it's a nightmare. So this one is like, it will get you there, other ones. All right, so that's how you extend W1, WP. And first we need to show linear independence. Let's do that, because we need basis. So you start with this relation. And the question is, how do you use induction hypothesis to get linear independence? So I should put constants here, A1, AM. So how do you get that A1 to AM or 0? So, yeah. So let me show, so this is the relation, and this is the induction hypothesis. Okay. You have to use one fact. How do you use this fact? Yeah, you just do it. So let's go back. So it says that NMI plus 1 of VI is 0. So NMI plus 2 of UI is 0, right? And here you have the UI. And furthermore, we assume that ordering, because it doesn't matter, they're constant, so they have some ordering. So M1, and then you start killing them off one by one. Okay? Maybe that's too complicated. This is too complicated. So an easiest way is you just, I don't know why I did this. This is I1 minus 1 VI. I think that's easier. I don't know why I'm killing myself. VM. And these guys were Li to begin with. Yeah, I don't know why I'm. But because I'm not happy with this approach, the one I like is where you take powers and you kill all of them except A1, and then A1 is 0. And then you keep playing this game and you kill each of the coefficients. That's my favorite way. This one I don't see it. It's like in the induction. This one I see it because you just factor. All right. The hard part is this WIs. So this is a trick. Do I explain it here? Yeah, okay. So again, we want to show that the full thing is a basis, right? And we got that the yeah, so we need to show that this whole thing is a basis. So we got the Li for the first ones. Now we have to get for the last part. And we're going to do the following trick. NWI is an image of n, just by writing it like this. But by induction, we have this result. Okay, this is the result by induction. So this is the magic here. So that means you can write NWI as NXI for some XI from here. Okay, we'll do this slowly. That's beautiful. And now I want to make a choice of a WI prime such that when you take its n, it will be 0. What choice should I make based on this? It's very dirty. No, it's dirtier than that. It's very dirty. There's no intelligence in this trick. Yeah, that's why it's dirty. You don't learn anything. Just a dirty trick. Yeah. Zoom people. Going once, twice. You just define it as the difference. Very dirty. Dirty. I told you it's dirty. I looked at it. I was upset. When I saw this, I was angry. I was like, this is dirty. I learned absolutely nothing. But I have to do this because it's an expert and it's made me to just upset. It doesn't. It makes no sense to me. But well, it does make sense that all it says is that this is row echelon. That's what's happening here. You took an xi from some of the columns or row, whatever you want to say, and you just did row echelon. You did subtraction of a linear span of these guys, right? So remember row echelon, it says you can move one row from another, and it can be a linear combination. So this xi is a linear combination of all this stuff from A. So like AK, N, M, K, UK, and so on. What? No, not from levels. That's the point. That remember, this is the dirty trick that's happening here is that the span of this guy is the same as the span of 0, 1, 1, 0. That's all is happening. That these two guys have the same span. Yeah. So you just killed off one of the common coordinates. That's all. Yeah. But it's like hidden in notation. All right. So why did we do this? Because we want to be in the language of cycles and chains. So just to remind you, what is a cycle? This guy is a cycle because nmi plus 2 ui is 0. And here the mi is 1 because n of wi is 0. So it satisfies that condition of being a chain. That so now, yeah. So now you go to your tableau and you just add a long stack of w's. So you have w1 tilde, wp tilde, because when you add by n once, they all become 0. So this is your new tableau. Yeah, well, that's what I said to study what happens when you extend. Each time you have to do like your number of yeah. Are you talking about the W's or what? Yeah. Yeah, P could be 1, doesn't matter. Like the number of guys you added. Yeah. Whatever P is. If it's just one guy, it's one guy. If it's not guys, you're done. So, but we know our kernel is, it was non-injective. So then we know there's stuff in there. Okay, questions? All right, so this was the meat of the proof. Now let's finish up with Jordan form. Okay, so Jordan form looks almost identical. with the main difference that instead of zeros, you have eigenvalues along the diagonal. So let's go. So you study this operator, t minus lambda ji, and this guy is nilpotent of dimension. Is nilpotent with this dj, when we talked about this a few weeks ago, that the maximum, that you hit the dimension of the space. So the nilpotency degree is at most dj, which can also be given by the algebraic multiplicity. So we will do some examples to give you quick ways to compute Jordan blocks without having to find the basis, because we don't have time in the test. All right. Let's do it. So we have this block. Yeah, so it's nilpotent, and yeah, so this is the matrix. So this is the previous result where we proved that. So this is, if you like, let me do it carefully here. So this is n of b, one of the bases, okay? So, which we defined as t minus lambda ji. So this is from previous result. Okay, that you can find the basis so that you can write it like this, right? I think that's okay. And yeah, okay, let's do it. So how do you finish from here? I remember I talked about this. I have deja vu. Jeez. So we have t minus, yeah, I remember this. T minus lambda j equal, so for some pj, is equal to this. How do you get the result that you can put diagonals, eigenvalues in there? I did do this, I remember. Or did I forget? Yeah, so how do you do matrix representation at the end of the day? You have t minus lambda I. Yeah, you have to evaluate some vector bk, and you get some combination of the bk's. Call it a. Okay. But now you can split this. You can have t of bk is equal to lambda bk plus this combination. So you have one matrix of lambdas. So you have lambdas plus the other matrix with the A's, which we know it has zeros and it has ones. Then you just add them, right? Matrices are added coordinate wise. Okay. So that's how you do it. So the meat of the proof was really getting this basis. Yeah, that's all the work we did. That's for that. All right, so that was the last proof we didn't see. And we'll just do example after example after example till your eyes blink. All right, let's start with the process. Okay, so here's a big matrix. It has to be big matrix, otherwise it's boring. And the number one thing you have to do is find the characteristic polynomial. I understand this is a big matrix. And we have no idea. No, stop it. So, so how do we find characteristic polynomial? You have to take determinant, right? So you do minus lambda. uh, minus lambda like this. And yeah, so you expand along, so you do your stuff like, I mean, it's disgusting, I'm not gonna do that. But you can, do you want me to do it? Is that okay? Do you, uh, yeah, so then, so huh? So you do this, you get a small matrix, and then you play the game, so you get uh, 5 minus lambda, then you get minus 1 minus lambda, and then you have the 2 by 2 matrix, right? So you have these two. So we have minus 3 minus lambda, 7 minus lambda, plus 2 times 12. So that's one term. And then you just have one more. That's it. So you have 1 times same thing, minus 1 minus lambda. And square it is the same thing, whatever you compute. Wait. No. It's actually easier. I made it hard. Yeah, I should carefully cross these things. So then you go like this, and then you have 9 times, so you cross this guy, and you get the same thing, okay? What did you know?
Something like that. I don't understand how you cost it.
So the way you do, so let's do, how do you do cofactor expansion? So each time you have to kill off an entry, right? So we did this, and so we left with a 3 by 3 matrix. We play the game again, and you get 2 by 2. Okay. Now, if you go to the next one, it's 0, and this guy is also 0, right? Because there's a 0 over here. Yeah, and then you go here, you have to do something. So you come here, and again, these two are 0. So you just cross this guy. And then these two are also 0. So there's no. And if you, so the reason it depends what you want to do. So this looks hard, but finding the eigenvectors is even harder. So, and the point is from here, you can get the, this is a, you want to find the eigenvectors 4 by 4 matrix. No, I'm just saying, like, with this characteristic polynomial, no, because he said, no, I'm looking at him. All right, so from here you can get your Jordan blocks. So you can read off the size from here. So you can have 3 Jordan blocks, and I think I draw them here, and it will be size. Okay, so I'll do it here. So you will have the guide for A2 will be a 2 by 2. So yeah, 2, 2, 0. And here we haven't decided yet, because it could be diagonal. You could have 2 eigenvectors, or it could be non-diagonal. So you have to put a 1. So this is still open. And A1 is 0, and A3 is 0. So you will have A2, A1, and A3. If you want to put it, whatever. So that's the other thing. So don't get tripped up. The ordering of the Jordan blocks with eigenvalues is irrelevant. So there's 2 different things. So if you have an important map, you really have to order them in decreasing length. Okay, so your cycles need to be decreasing. So M1 needs to be bigger than MK. So you have a big matrix and then a small matrix. Okay, this is for the important maps. This is a little bit harder. Each block corresponds to an important map. So you should see this as a fractal. So each of them has its own important map. And it doesn't matter how you order them. Okay, we'll do examples to see what I mean, but the point is, I might as well, let me do it here. So you could have, let me do something stupid, 3, 3, 1. Okay. So, like this, then let me make it bigger. 1, 1, and then let me put a 4. So this is one Jordan block, this is another Jordan block, and this is another one. Okay? You could also have written this as 2, 2, 2, 1, 1, 3, 1, 3, and 4. Okay, they're the same thing up to permutation. Okay, they're both called Jordan canonical forms. So you can have, I think this is in your homework, isn't it? No, it's in your last homework, 5. It wasn't in the homework. So this is in homework 5, so please do the question, because it's very relevant. And the point is, since you have 3 Jordan blocks, it's like, I don't know, what 3 to the something, some number, some factorial, like 3 factorial.
Is that Nilpotent? Because wasn't the T minus lambda I Nilpotent? But we don't get the T here.
Yeah.
So that's not Nilpotent.
Yeah, but I'm saying the way you get it is you start with this important map and then you just add the aggregate. Yeah. Otherwise, but if it's not, it's, yeah. But I just want to say this is not, well, it's very easy to confuse because like the important maps have to be decreasing. These guys do not have to be. So I hope I. Right. Question? All right. So yeah, the problem is we don't know if our map is. Oh yeah, question. Wait, you asked why A1 is 0? Oh yeah, because I don't know what I'm talking about. I'm still thinking of, yeah. Okay, thank you. So yeah, we don't know whether to put 1 or 0. When can I put 0? In what case can I put 0 there? If I know what? If 2 is equal to what? Dimension of who? Yeah. Yeah, E2. And we will show that this is not the case. So that will be it. Okay. So if you sit down and do it, you just subtract the -2. You find that the only solution to the system is 13000. Okay, so what I'm saying is a minus 2I is 3 minus 1, 9 minus 3, 7 minus what is 7 minus 2? 5. and then minus 5. Okay, and you have x, y, z. You get 3x1 minus x2 is 0. And you get 5x3 minus 2x4. And 12x3 minus 5x4. Then if you do that stuff, x3, x4 is 0. And you get okay. So okay, because from here you can see you have 3x1 is x2. So just put x1 to be 1, and x2 is 3. Right. So can someone now tell me what should I put in my first block? Yes. Good. Finally, I draw the table here. How to further find the Georgian? Oh, yeah. Well, before I do that, let me draw the table. So from here, you should be able to draw the table. Okay. So let me tell you how it is. Right. So first, caution. Again, you should think about this as 3 different important maps. So don't get mixed up that you can have a Young block for the whole thing. You cannot. You have to do it for each eigenvalue. That was a question in the final, but I asked it to be removed because I thought people would get tripped up. Probably wrong. So for lambda equal 2, unless it was added back. Okay, lambda equal 2, you have 0, 2, 1, 0, 2. And I have to draw you the table. Right, this is 2 by 2. That's the thing, because I don't want to give the answer. So this is 2 by 2, and
It's like it has to be one row or two horizontal.
always will do it by hand. So you have to forget the 2's and just look at the Nilpotent map. And first we have to find the nilpotency degree. But the nilpotency degree is 2. So you get 2 boxes on the first row, and you're done. And while you're done, so let's first verify that this is indeed 0. So you have 0, 0 times itself. And if you multiply it out, you get the 0 matrix, right? Right? So you have 2 boxes. So K is 2. So 2 boxes, but the total number of boxes is also 2. Because what is it? D2 is 2, the dimension of the eigenspace. So you're done here, okay? There's 2 boxes, because it could have been this way. Oh yeah, how could you get this? Yes. Yeah, exactly. So I was supposed to say. Yeah, so if you were diagonalizable, you will get 2 boxes like this because your nilpotency would be 1. Because that's another way to think about it. All right. And yeah, for the other ones, it doesn't matter. It's easy. It's just 1 box. You only have 1 dimension. Yes. Oh, yeah, because, yeah, don't do that, because they have no connection to each other. There's no connection. They're not like, there's no, yeah, don't get mixed up. Uh, um, there are different nilpotent maps. There's no like ordering. All the stuff we did were for nilpotent maps. Yeah, it was like one nilpotent map. Here we have three different nilpotent maps. But you will also be asked to find the basis, so I'll do it here now. Some questions that will just ask Jordan block, so you can do it quickly with the characteristic polynomial. Other questions they will ask you then for the basis. So here's the algorithm. I'll do it again. First, you need to find the eigenvectors for the whole thing. And so I did the computation for that matrix that we had. I found the eigenvectors, but the dimension is 4. So I'm missing one vector. So I still have to do a little bit of work to extend. So for which vector do I have to do the work? Yes. Yeah, so I have to do the work for the lambda 2, B2, because multiplicity is 2. So K2 is 2. So I'm missing one vector. I need to expand. And the way you get the other guy is you solve this system. Okay? And yes. So you solve the system, and if you solve it, you get this. What should I say here? And so why do you need to solve this? Because remember, K2 is the kernel of A minus 2I squared. Okay? We already have the kernel of A minus 2I is this guy. Now I'm finding an X that is not in here, but it's in here. So you're trying to find some guy in the kernel of A minus 2I squared, take away kernel of A minus 2I. Yes. Well, that's the thing. It might happen sometimes that X is V2, like a scalar multiple. Like you might have options. You might have three numbers, and you will have to pick the one that's not V2, which would be easy, you'll see. All right, so then, yeah, that was it. You get your basis. All right, we'll continue tomorrow. What?
I'll make it up. I'm trying to do some triage.